Hello everyone. In this video, we're going to talk about chapter 12, section 12.4 and 12.5. We are going to look at the general curvilinear motion and the rectangular components of the kinematic vectors. Section 12.4 talks about general curvilinear motion. When the particle moves along the curved path undergoes a curvilinear motion, since the motions are usually 3D in 3 dimensions, and then the vectors are usually used to describe the motion. When the particle moves along the curve defined by the path S, so the position of the particle at any instant, we're going to use this vector R to describe the position. And remember, since it's a vector, we're going to need magnitude and direction. This is to describe the vector. Magnitude and direction may changes with time. Okay, at any moment, the magnitude could change, the direction could change as well. And if the particle moves along the curve during the time interval delta t during a period of time, the displacement is defined by the vector subtraction. So I have a later position r prime minus the initial position r, and then that gives me the delta r. And keep in mind that this is a vector subtraction instead of the algebraic subtraction. So, other words, in the diagram, it's showing delta r gives you this portion right here in your triangle. Velocity represents the rate of change of the position, so how fast I'm moving from one location to the other. Average velocity is defined as the particle during the time increment delta t. So average velocity in your equation equals delta r, change of position, over a period of time, delta t. Instantaneous velocity is the time derivative of a position. So in other words, instead of using the overall total position change over total time, instantaneous velocity will be derivative of the position with respect to time. And then the velocity vector v is always tangent to the path of the motion. Magnitude of v is called the speed. Since the arc length delta s approaches the magnitude of delta r as t approaches zero. So when the time at that frac of that second, when the time is really, really small, arc length delta s will be almost about the same. It will be about the same delta r when t is a really small number, t approaches zero. Okay, the speed can be obtained by differentiating the path function v equals ds dt. And so note that this is not a vector. Acceleration represents the rate of change in velocity. So in other words, how fast the velocity change. It's the change of velocity over a period of time. Average acceleration, if we need to find the average acceleration, it will be change of velocity over divided by the change of time. Over this period of time, how much velocity changes. Instantaneous acceleration, again, just similar to the velocity, instantaneous velocity that we talked about on the previous slide. Instantaneous acceleration will be the time derivative of the velocity. So in other words, if I take the velocity, first derivative of velocity with respect to time, that will give me the acceleration. And go backward one more step, that means if I take the position vector, second derivative of the position vector, that will give me the acceleration. Take the position vector, first derivative gives me the velocity, second derivative will give me the acceleration. And keep going. A plot of the locus of the point defined by the arrowhead of the velocity vector is called the hadrograph. The acceleration vector is tangent to the hadrograph, but not in general, but not tangent to the path of the function. Now, section 12.5 talks about the rectangular components of the curvilinear motion, and it is often in 3D or 2D in motion. It's often convenient to describe the motion of the particle in terms of XYZ rectangular components relative to a fixed frame of reference. Position of the particle can be defined at any instant by the position vector r equals xi plus yj plus zk. So I have the xyz component along the ijk direction. And then the xyz component may be a function of time. All of them or some of them may all be a function of time. X can be a function of time, x of t. Y can be a function of time, y of t. And then z can be a function of time, z of t as well. Magnitude of the position vector r will be equal to x squared plus y squared plus z squared, and then that to the zero to the half power 0.5 power, meaning I'm taking the square root. Square root, this means I'm taking the square root of x squared plus y squared plus z squared, gives me the magnitude of the position vector. And then direction vector, we sort of studied this in statics. Direction vector, direction of r is defined by the unit vector. UR equals 1 over r times r. So be careful over here. You see these two r's, they were somehow written slightly different. This r right here, this one, ooh, hold on. This r, let me do it a little better. This r right here refer inside the parentheses and under on the denominator 1 over r refers to the magnitude of the position vector. And this r is written in the 5-degree angle. This r right here is referred, let me use a different color. This one right here, this one right here refers to the position vector. So in other words, the green one is your vector. I'm using the vector divided by the magnitude of the vector. The red one that I underline is the magnitude only. Okay, the green one that I circle is the vector. The vector divided by its own magnitude of the vector, that gives me the direction of the r defined by the unit vector. And then vector velocity is the time derivative of the position vector. One more time, if I take the position vector first derivative of the first derivative of the position vector, that will give me the velocity vector. And then since the unit vector ijk are constant in magnitude and direction, the equation, we're going to write it v vector velocity vector v equals vx on the I direction plus vy on the j direction and vz component on the k direction. And then where Vx equals dx dt, so I am taking the position vector, the derivative of the position vector derivative on the x direction, that will give me Vx. Okay, keep going. Position vector taking the first derivative on the y direction, that gives me the Vy. And then the position vector on the z direction, that gives me the Vz on the velocity on the z direction. Now this g here, a little funny printing from the PowerPoint slide, all the g here, it really should be a dot. Okay, meaning I'm taking the first derivative, one dot. And later in the PowerPoint slide, you will see two g's on top of a letter. That means two dots on top of it. That's the second derivative. Right now, you see one g there. It really what it wants to show you is the g x dot, y dot, z dot. That dot means I'm taking the first derivative. Okay, keep going. Magnitude of the velocity vector v equals vx squared, taking the x component vx squared, taking the y component vy squared, taking the z component vz squared, and then I'm taking the square root of all this. And then the direction of the velocity is tangent to the path of the motion. Acceleration, we're taking the derivative of the velocity, gives me the acceleration. Or I'm taking the second derivative of the position vector, that will give me the acceleration. And one more time, first derivative of the position gives me the velocity, and second derivative of the position gives me the acceleration, or first derivative of the velocity gives me acceleration. Okay, so overall, this is what's going on. First derivative of the velocity or second derivative position, that's referring to the same thing, that's acceleration. Acceleration, I got ax on the I direction, ay on the j direction, and az on the k direction. And where ax is, look, that g right there means I'm taking a dot. I'm taking the first derivative of the velocity on the x component, that gives me ax. And again, if you want to start from the position vector, that will be the double dot. You see 2g there, that what it means is double dot. So the second derivative of the position gives me the acceleration. And then on the y component, 8y, that will be velocity. On the y component, it should be vy 1 dot. This one should be 1 dot here. I'm taking the velocity first derivative of the velocity, that gives me acceleration, and then second derivative, two dots. Second derivative of the position, which is equivalent to the first derivative of the velocity, that gives me the y component of the acceleration. Similarly, you have the z. Az is the first derivative, z component velocity, first derivative gives me acceleration, or z component position vector, second derivative, that gives me the acceleration on the z component. Now, similarly, if I want to look for the magnitude of the acceleration of the acceleration vector magnitude, you take ax squared, ay squared, and az squared overall, add them up all together, taking the square root, that gives me the overall magnitude of the acceleration. And keep going. The direction of the A is usually not tangent to the path of the particle, and compared to the direction of V, tangent to the direction of the V usually is tangent to the path of the motion, but acceleration is not tangent to the path of the particle. Let's take a look at two examples together. Example number one, I have a box slice down the slope described by the equation. So I have the y position vector y 0.05 x squared in meter, where x is a meter. So in other words, y is a function of x. And I know Vx, x component of the velocity, -3 meters per second. And then I know the x component of the acceleration, ax, is -1.5 meters per second squared at x equals 5. We're looking for the components of the velocity and the acceleration of the box at x equals 5 meters. Put them together. I am going to, so y is given to us, position vector 0.05 x squared. I am going to take the first derivative of that y, okay? And over here, notice that x is a function of time as well. This is there's a chain rule over here, right? Taking the first derivative with respect to time, not x. I'm taking the first derivative of y with respect to time, okay? And x is a function of time as well, so there's a chain rule over here. I have 0.05 x and then x dot, okay? That g again stands for dot. I'm taking the first derivative. And then simplified it a little, that gives me 0.1 x dot for x times x first derivative. And then if I taking the derivative again, I need to take the derivative again, y double dot, second derivative of the position vector, or first derivative of the velocity vector, same thing. This gives me the acceleration component. Okay, so now over here, in other words, I am taking the derivative. I am taking the derivative of first derivative of this thing, which is the velocity. It's already this what I'm underlying purple here. That's already the velocity vector. So in other words, I'm taking this one, take the derivative, first derivative again. That will give me the second derivative, which will be the acceleration. Okay, and again, x is a function of time. So this will be a product rule over here. Okay, so that part plus that part. Okay, x dot derivative of x, and then x that gives me x dot on the first one, and then x another x dot you already have, and then 0.1 x dot, and then the second component will be x double dot. Okay. So substituting the x component of the acceleration velocity, x equals 5. So over here, we know the x component, we know that Vx, this is equivalent to x dot. We know our Ax, that's equivalent to x double dot. Okay, plot this two, plot that -3 and -1.5 into our equation. So this is my what is it called? X dot, y dot. This is my y double dot, right? We're gonna plot that in. A little complicated here, but no panic. We know x dot, that's my velocity, -3 meters per second. If you forgot what that is, look, it's given to us. This is Vx, which is x dot. And this one right here is this one right here is x double dot. Acceleration is x double dot. So I know the x double dot acceleration, this is given to us at x equals 5. Plug that in. This was calculated this two, both this one and this one. The two equations was from the previous slide. I am plugging in the value of x and x dot. I am plugging in the value of x and x dot to get the y dot, which is the velocity component on the y. And then the y double dot, I'm plugging in x dot, and then x double dot. That will give me y double dot, the acceleration component, on the y. Okay, and overall that gives me at x equals 5 meters, I know the y value of the velocity, ay, and the y value of the acceleration as well. Okay. Next example, very similar. Okay, we're gonna take a look at them. Particles travel along the path. It's given to us y equals 0.5 x squared. This is at the time when time equal to 0, x equal to 0, y equal to 0, z equal to 0. We're looking for the particle distance and the magnitude of its acceleration when t equals 1 second. If velocity 5t, if velocity is a function of time 5t, feet per second, where t is in second. Okay, so now we're going to break it into the x component and the y component. We separate the x and the y. Problems given to us y equals, let's take a look at the x component first. We know that x component of, since x component of velocity is already given to us. Vx equals phi t, okay, right here. Vx, which is x dot, first derivative of the position, gives me the velocity. Okay, phi t, this is given to us, phi t feet per second. Okay, so we know that phi t, I'm going to plug in t equals 1 second. At t equals 1, what's my velocity? Plug in t equals 1. That gives me velocity at t equals 1 is 5 feet per second. There's my velocity. Once I have the velocity, in order to find the position, I'm going backwards. That means I'm taking the integral. Integral phi t dt. Okay, so going from 0 to t, I know that position vector is a function of time. Taking the integral of phi t, I got 2.5 t squared. Okay, again, in this function, in this position function, I am plugging in t equals 1. Plug in t equals 1, that gives me x equals 2.5. Okay, that means at t equals 1 second, the location, the position on the x component position vector is 2.5 feet. Acceleration, we're taking the vx. We're taking the vx right here, taking the derivative of my velocity vector. So taking the derivative of the velocity vector with respect to time, that gives me 5, only in the 5, right? 5 feet per second squared. That is the acceleration. And regardless what time that is, at time t equals 1, since like acceleration is going to be a constant, but regardless what that is, at t equals 1 second, my acceleration is going to be 5 feet per second squared. Next, we're going to take a look at the y component. This part is given to us. Y is a function of x. Okay, we know that x is, we know that from the previous stat. Let me use a different color. We know that from previous stat. At t equals 1 second, x is this much, 2.5 feet. Okay, so simply just plug it in. If we're looking for the position factor, so 0.5 x squared. So you're going to take 2.5 squared times 0.5. That will give you 3.125 at t equals 1. Velocity, we're going to take this one. First derivative of the position gives me the velocity. Okay, again, we're taking the derivative with respect to time. And x is a function of time as well. So there's a chain rule from your calculus. So this gives me 0.5 2x x dot. And again, that g on top of that letter stands for the dot. This stands for the first derivative. Okay, so 0.5 and the 2 combined together, that gives me y dot, first derivative of that y equals x times x dot. Plug it in. Really, what you do is plug it in. There's my x. I highlighted in green up here. I have my x from the x component 2.5. You take 2.5 times x dot, which is this one. Okay, that will be x times x dot, 2.5 times 5. That gives me 12.5 feet per second. This is at time t equals 1 second. And keep going. Lastly, a acceleration on the y component, y double dot, second derivative of the position. Okay, or you can take a look at it as if it's the first derivative of the velocity. So in other words, you're taking this term, take the derivative with respect to time. Okay, and since you have x and x dot, it's going to be a product rule. Okay, so this gives me the product rule. That would be, actually this would be a double dot right here. Okay, so we're going to take that will be double dot right here. This one will be, it should be two g's there, double dot. So this two will be one dot. No. Okay, so we're going to take x dot times x dot. So you take 5 times 5 plus 5 times 5 gives me 25, right? First term, this term right here, 5 times 5 is 25. And then second term here, that's x times x double dot. X times x double dot, which is 5 times x double dot is 5. And then x is going to be, where's my x? Right here, 2.5. Okay, so really, you can look at it from the previous step as well. 12.5 plus 25. First one, this part is 25. This part right here from the previous step, 12.5. So together, 37.5 at t equals 1. And then if I'm looking for the position vector, really all we're going to do next is putting them together. I have the x component and the y component separately, right? Velocity, acceleration, and position. All we got to do is put that together. First one is your position vector. Position vector says, let me use a different color. Position vector says I have 2.5 on the, sorry, I meant to use black. I have 2.5 on the x component. I have 3.125 on the y component. Look, 2.5 on the x component, 3.125, what? 3.125 on the y component. And then putting these two together, if I'm looking for the magnitude, I do square and then square root. Square root of 2.5 square and then square root of 3.125. These two together gives me the magnitude of the position. And then the acceleration, same thing. We're referring to the x component of the acceleration, 5 feet per second square. And we're also referring to the y component. We're referring to the y component of the acceleration, putting these two together, 5 on the x, 37.5 on the y. 5 on the x, 37.5 on the y. These two together, that will give me the acceleration. Okay, if I'm looking for the magnitude, and you take the x component square, y component square, and then taking the square root, that will give me the magnitude overall. Okay, this is all I want to share with you in this section. Thank you for watching.